Hi everybody, and thanks for joining my talk on InvaliDB, scalable push-based real-time queries on top of pull-based databases. I'm Wolle from the German company Backend, and today's talk will be about InvaliDB, which is the system that we've developed at Backend to provide scalable real-time queries. This talk will be divided into 4 major parts. The first one is the introduction, where we talk about the actual problem we're trying to solve here and why it's difficult to provide real-time queries to begin with. Then we'll talk about related work. So that means we'll talk about other approaches for providing real-time queries, and we'll uncover what the issues with these approaches are. In the third part, we'll talk about InvaliDB's design. So we'll explain what we are making different. And in the fourth part, we'll discuss applications of our design, and we'll talk about what we're planning next. Okay, so let's start with traditional databases. And for illustration, let's talk about a real-time application that displays basically the data that is in the database and provides real-time updates. So consider a simple token application that only displays all of the circular shapes in your database, and then just think of a database as storage of different shapes. So things get written to the database, and when the application starts, it displays the current state. So currently there are no circular shapes, and we don't see any of them in the user interface. But over time, we get eventually like this blue bubble there. And when we refresh the user interface, then we also get an update. But the thing is that sometimes things get written and the application is not refreshed. And then we have a divergence between database state and application state, because the application has to explicitly ask the database for the change, or basically the current state. And when it does that, it gets the state, but in a very inefficient and slow way, because everything is sent from the database to the application, even if part of the state, like the blue bubble here, is already known at the client. And it's very slow because the application has to ask for changes. And if the application, for example, only polls once a minute, then you have a 1-minute staleness window there. What you actually want to have in this kind of application is a real-time database as a storage backend. So in this case, the application doesn't just fire up a query initially, but establishes a persistent connection so that the database knows, okay, this is the kind of query that I need to keep up to date. And whenever there is something relevant to the query results, so namely circular shapes, then the database just transmits them immediately and without any delay. So that is just very efficient because it doesn't transmit the same data twice without a good reason. And it's also very fast because updates are transmitted immediately. The problem with real-time queries is that they are very resource intensive to provide. So just imagine you have a single real-time query, and now you have a single update operation hitting your database. Then you need to consider, okay, the item that was updated, is it a match to the query now? And did it match the query before the update occurred? And judging by these points of information, you have to deduct whether the result changed, or whether an item was added, or whether an item was removed. And depending on the number of queries that are currently active and the right throughput and the query complexity, matching every query against every incoming update operation can just become prohibitive. And that's the reason why triggers or event condition action rules and materialized views are also very expensive to provide for a database system. Okay, so now we've set the scene for what a real-time query is and why it's difficult to provide. Let's talk about how current technology is addressing this problem. There are 2 prevalent mechanisms for providing real-time queries. One of them is called Poll-and-Diff, and the name already tells you what it does. So in the example here, we have different application servers and different users, and the users subscribe for real-time queries at the application servers. So whenever an application server receives a write operation, it writes that off to the database and also checks whether any of the query subscription that the server itself handles is like affected by this write operation. And if so, it sends out the change notification. This is pretty simple, but the problem is that sometimes the server on the right will receive a write operation, and the server on the left doesn't really know that that happened. So to discover changes that are written by other servers, it polls the queries that are active periodically. So for example, the Meteor default is 10 seconds. And then it gets all the results, checks whether anything changed to the last known result representation, and sends out the changes accordingly. This works functionally, but the big problems here are, first, you have a giant staleness window. So if you poll every 10 seconds, then your results might be laggy by 10 seconds. And you also have absolutely no read scalability, because if you have many concurrent queries, so many users, even if nothing happens on your database, then your system will be clobbered to death with these polling queries. But there's another approach that avoids the periodic polling, and the basic idea, changelog tailing, also tells you what it does. So the idea is that all the application servers subscribe to the entirety of the database changelog. So if, like in the example earlier, the server on the right receives a write operation, it writes it off to the database, and the other server doesn't have to poll for changes because the change is delivered with the database change stream. So the app server essentially pretends to be a database replica. Now the app server on the left has the update, can check whether any changes occurred to the subscribed queries, and it can send out all the notifications. And this is awesome because it avoids the latency overhead of polling and also avoids the read scalability bottleneck. But the problem is that if you really need database sharding, then writes are distributed on the database level, but the changelog broadcast, because every app server is subscribed to all of the database shards to receive all the changes, this broadcast will just break your application because you cannot effectively shard your application even if you're using a sharded database. And that's a problem because this essentially means, or effectively means, that you have no write scalability whatsoever. As you can see, most systems today use either Poll-and-Diff or changelog tailing. Firebase and Firestore are the exception, as they use unknown proprietary approaches, but the bottom line of this table is that no system provides simultaneous read or write scalability irrespective of the approach that they are using. And that's why we developed InvaliDB, because InvaliDB can provide read and write scalability at the same time. In the next section, we'll talk about the InvaliDB system model, so how subscriptions and change notifications work, and how the matching workload is distributed internally to achieve simultaneous read and write scalability. When an application registers a real-time query with InvaliDB, it sends the query to the app server, and the app server executes it on the pull-based database. And the result is not given to the user, so to the browser, for example, but rather given to the InvaliDB cluster. So it's sent to the event layer, which is kind of a message broker, and then we have this distributed cluster of nodes on the left that just registers state, and when everything is done and ready, it sends out the initial result for the end user, just as a sign that this subscription is ready now. And whenever something gets written, could be by another user or by another process, could be received by the same application server or by a different one, doesn't matter. This write operation is applied to the database and also given to the InvaliDB cluster, where it is checked against all currently active real-time queries, and then any change data deltas are sent out if there are any. So this architecture has two big advantages over the other approaches discussed earlier. One is that real-time and OLTP workloads are decoupled. So we don't have the matching within the application server. So, an overload in the real-time workload cannot bring down the application server. That's a big pro. And also, we can scale the InvaliDB cluster just to beef up our real-time capabilities, which is not possible if you have anything on everything running on the application servers themselves. And another big advantage is that since all the resources are completely decoupled through the event layer, we can exploit resource pooling and multi-tenancy. So adding new clients is very cheap, and we still have a big cluster running behind all the clients together, which gives us the ability to buffer load spikes and such. But the magic obviously happens within the InvaliDB cluster. So just consider we have a component for ingesting queries and for ingesting writes, and then we have a bunch of nodes, 3 by 3 in this example, for matching queries against write operations. What we do first is we partition all the nodes into query partitions. And when a query is registered, we give all the nodes in one of these partitions this query. So now 3 nodes are responsible for keeping this query up to date. And for writes, we do the same. So we partition everything into write partitions. And when something is written, we determine the write partition and then give the write operation to all the nodes in that partition. Now you see that there's an overlap between all the query and all the write partitions. So when there is a change to be detected, we know that one of the nodes will generate and send it out. But we also have responsibility of only 1/3 of all queries and 1/3 of the write throughput per node. So no node is actually responsible for all the writes or all the queries. And if we need, for example, to support more concurrent queries, we can just add more query partitions there, or we could increase sustainable throughput by adding more write partition nodes. So that gives us simultaneous read and write scalability. And while talking about this, I didn't once mention the query engine. So that's why we implemented it in a pluggable way. So we could currently support MongoDB, and that's what we do, but we could also support SQL, for example. That makes the approach very generic. We implemented InvaliDB at backend, and we used the distributed stream processing system Storm for implementing the distributed query engine because it's just unmatched in terms of low latency, just as Redis. And that's why we chose Redis for the event layer for communication between app server and InvaliDB cluster. And we implemented everything with the MongoDB database because it's the database underneath backend and because it's just a very expressive NoSQL database. It just shows real-time queries can be expressive. Okay, now finally, let's discuss application scenarios for our real-time database. Currently, there are 2 main use cases for real-time queries at backend. The first one is providing this functionality to developers. So as you can see here, we have an interface for pull-based queries and one for real-time queries, and they are both essentially the same. You just use a different keyword here. So you have your query object, execute a query function, and provide a callback function that is called whenever there's a result. And for the pull-based query, it's just called once because there only is a single result. And for the real-time query, it's called whenever the initial result is returned or when there is an update. So this is a very easy way to execute and create real-time applications. The second use case is consistent query caching, essentially for improving performance of pull-based databases, because InvaliDB was initially designed for invalidating database queries, hence the name. And what we do here is that we make even complex database queries cacheable. So for example, user searches for products in a web shop, and then deploy InvaliDB to detect whether anything has been added or changed or removed in any of the currently cached database queries. And if that's the case, we just have InvaliDB invalidate all the caches. So that lets us cache things that you would normally not be able to cache because we can track whether or not the results have changed or not. We evaluated the potential gains of this use case in our VLDB 2017 publication and found that both latency and throughput of traditional pull-based queries can be improved by several orders of magnitudes here. Yeah, to sum everything up, we've seen that traditional pull-based databases are not the best choice for reactive or real-time applications because they require you to execute the same query over and over, which is both inefficient and pretty laggy. And then we've seen that push-based real-time queries with InvaliDB are more efficient because they enable you to just specify your query, then keep the persistent database connection open and receive changes whenever they happen. So first, you have a continuous stream of updates here. Then our approach is legacy compatible, so you can make it work with your application stack, even when it is built on top of a traditional pull-based database. It's very scalable and fast. And our expressiveness is roughly that of MongoDB. So it's essentially NoSQL capable. Okay, and it's very developer friendly because you can just use the same query semantics for both pull and push-based queries. Yeah, that basically concludes my talk. Thanks for your attention. And if you have questions or comments, please drop us a line at volle@backend.com. Thanks very much.